Hello, good afternoon. Here we are for another lovely session of CENG 4412 Steel and Concrete Design. Okay, so I'm going to hold an unusual lecture on a Monday, not one that I'm recording not a session that I'm recording as a continuation to a previous lecture, but actually an entirely independent lecture for a Monday here instead of our Tuesday-Thursday schedule. And I'm doing this to make up some time we lost through the semester, through this, that, and the other thing, the hurricane, etc., etc. Okay, this is going to be the 15th lecture in the series. This will have 2 or 3 parts, I imagine. But this portion will be looking at the immediate deflections of reinforced concrete beams. So my objective here is to talk about the theory and application of immediate deflection of reinforced concrete beams. So previously we have looked at the strength and serviceability design for steel members. And also we've looked at strength and we've looked at strength, but not serviceability, not deflection for reinforced concrete members. So I wanted to cover, now I could have done this, but I could have done serviceability back when we looked at concrete beams in terms of strength, but I really like introducing the serviceability for steel rather than concrete first because the deflection for concrete beams is a bit more complex than it is for steel beams. So let's begin here. So deflection here, and as we discussed previously in the serviceability philosophy video, this is going to be based on service loads. So deflection, and we could talk about deflection of beams and slabs and other things, but we're going to be concerned primarily with beams today. So again, with deflection, we are looking at, we refer to this as serviceability, so we're using service loads. Serviceability and service loads. So service or unfactored loads. And where this is found, well, it's found in Chapter 24 of the ACI Code. So this is found in Chapter 24 of ACI. And we're going to use the exact same approach of delta, deflection actual, is less than or equal to delta allowable. The same thing as we did when we looked at steel beams. And so the allowable deflection is actually fairly simple. The allowable, you can find your ratios, your L over 240, L over 360, L over 120. Depending what you're allowed to use, the delta allowable is found in, you simply look at a table, and depending on what type of structural element you have, that's going to determine what allowable deflection you have, both immediate, long-term, etc. So delta allowable, the allowable deflection, this is found in table 24.2.2 of the ACI code, and in my edition that is on page 400. But it might be slightly different for yours. Okay, something also we need to keep in mind for deflection is that now for steel, there's only one form of deflection. We don't talk about immediate versus long-term deflection. But concrete, as we've discussed, it's kind of a lazy material. It creeps, it shrinks, it sheds load, etc. And so there is there's immediate deflection, which is going to be your, well, immediate deflection. Immediately after you apply a load, there's a certain drop in height, there's a certain stretching in length, all these sort of things. And so deflection for concrete, it comes down to 2 things. Concrete, we have immediate deflection and long-term deflection. Immediate deflection and long-term deflection. And long-term deflection. And in this video here, we'll be concerned primarily with the immediate deflection. It's complicated enough. Immediate deflection and long-term. So this is from, again, as a reminder, the immediate is from the immediate application of the load. You apply a load and you watch how much it deforms, and you measure how much it deforms. That's the immediate deflection. Long-term is the deflection, the further deflection you get as a result of load shedding, of creep, of shrinkage, etc. Okay, so I want to talk about immediate deflection today, though. So immediate deflection is going to be a function of 4 things. Immediate deflection equation, the immediate deflection equation, so in order to find deflection, we need 4 things. So 4 components of deflection. The 4 components of deflection. Well, immediate deflection anyway. She's all right. Immediate deflection. Of immediate deflection. Well, the first thing is going to be the beam length. Longer the beam, the more deflection, and of course it's not a linear sort of relationship. It's a third or a fourth power, that sort of thing, depending on whether you're dealing with distributed or point loads. So beam length, oh, not bare length, beam length. And often in design this may be given, at least in this class, when I give you a beam design, that's often just going to, if I ask you to design look at the deflection of concrete beams, usually that's given, but of course in real design that's not given. 2 loads. The applied loads, this can be from ASCE, ASCE 7, a combination of ASCE, static, structural analysis, etc. Structural analysis, etc. Whatever your favorite flavor of structural analysis, software, etc., etc. And then we have 2 things. So these are both outside the ACI code, but the other 2 components, the material and the geometry of the section, this is something ACI really talks about. So deflection, as we learned previously, is going to be a function, maybe not as we've learned previously, but as we saw previously, is the result, just like a strength design, deflection is a function of both geometry and material properties. So we'll have certain section properties like moment of inertia, and that's a section property of geometry basically. And then we also have material properties. For strength, the material property is yield strength, ultimate strength, etc. But for our deflection, our material property of note is modulus of elasticity. So modulus of elasticity, and we'll talk about each of these things. Modulus of elasticity. And each of these is fairly complex. It's a little bit more complicated than it would be for steel. And then moment of inertia. So concrete as a composite material does not have one simple modulus of elasticity. Steel is nice and easy. You can just say, oh, steel, everything there is 29,000 ksi. No problem. No, we don't have to think too hard about it. Moment of inertia, then we can just calculate. Even the moment of inertia, we can calculate relatively simply. But for for concrete design, this all gets quite a bit more complex. And so we need to use ACI 318 in order to calculate each of these things, or determine each of these things. So the first thing I want to do is look at modulus of elasticity. This is the easier of these 2 things. So modulus of elasticity, concrete being a rather complex composite material does not have a single modulus of elasticity. It has other things. It has a more complex relationship. In other words, it doesn't have a nice linear zone for the modulus of elasticity. Where the stress strain pot remains linear for a long period of time. It has a changing slope, a continuously changing slope. Well, I should back up and say it will have a linear region. It will definitely have a linear region, but more in different samples of concrete will not have the same modulus of elasticity. We need to predict it based off of a usually F prime C. Although I suppose you could directly measure it as well, and there are ASTM standards that you can do that. But anyway, usually we just use the formula present in the manual, in the ACI code, to calculate it based on F prime C. So, but anyway, that aside, EC, capital EC is the term that we're going to be using, or that we see in the ACI code. And this is simply the modulus of elasticity of concrete, of your given type of concrete. The modulus of elasticity of concrete. And I'm definitely giving you the kind of Cliff Notes version here. There's a lot of provisos and exceptions and other design considerations, etc., that will that we don't necessarily have time to get to in this course. But when you're actually working as a design engineer, you do need to read of those and be aware of them to make sure what you're doing is applicable. Okay, but anyway, so like I said, concrete does not have one overarching uniform modulus of elasticity, and so instead, you need to calculate it based on one of 2 formulas. The first one is the formula EC is equal to WC times to the 1.5 times 33 root F prime C, square root of F prime C, and this is equation, this here is equation 19.2 19.2.1a. 19.2.2.1a, and where WC is the weight of your concrete. So if I go here to, if I go to that section of my manual at 19.2.2.1a, let's see if I can find this here. I'll give you a page citation. 19.2.2.1a, and that's going to be on page, let's see, that looks like page 315 in my edition, maybe slightly different for yours depending on printings and such. But anyway, WC is the weight of your concrete, and then this is, you feed this in pounds per cubic foot, and this returns a result in, this is in PSI. You return a result in PSI here, or you input a result in PSI here. Here, let's see, and the final result as well should be in PSI, I believe. Yeah, I believe that makes sense. So, example, if I run a calculation here, if I put in, for the next formula, I put in, say, 3,000 PSI, 57,000 times square root of 3,000, and we get 3,122 PSI, which is a bit low. Or is that the result in KSI? Let's see here. Let's go back to our main list of variables here, and we see EC. Actually, that is the modulus elasticity of concrete in PSI, so that does work. Okay, so 57,000 times that many PSI. Oh, actually, no, that's returning 3.1 million. So that is good. So about 3,122 KSI in turn. Okay, so that is in PSI, and this also is in PSI. Where did my marker here go? Just a second. Okay, let me go back here and here. And this here is also in PSI. So you do have to be very careful with this, as I just illustrated. You have to be very careful in terms of units. These are empirical formulas, and so you do need to make sure that you're using the proper units, you're inputting the right units, etc., etc. And so this equation here is for all forms of concrete. This is the basically the gamma of the concrete in pounds per cubic foot. But and so you can use this formula even if you have very lightweight concrete. But if you have normal weight concrete, and this is basically for concrete with a gamma specific weight between 90 and 160 pounds per cubic foot. Anything below there, you have to start using other equations, or maybe even preferably directly test it. But that equation is only valid between 90 and 160 pounds per cubic foot. Or I should say, I say gamma, but it's also WC here. But for normal weight concrete, your typical bog standard normal weight concrete, you can just go and say, okay, well, this formula collapses to EC is equal to 57,000 times the square root of F prime C. Times the square root of F prime C. Again, this is in PSI, and this is in PSI. And the citation on this is just the next formula after the previous one. This is going to be 19.2.1a. Okay? So, here, now notice, we're only considering the, now this seems a bit odd. Notice that I'm mentioning it, the only modulus elasticity that I'm concerned with is the modulus of elasticity of the of the concrete. I have not talked about the modulus of elasticity of the steel. And so we know, of course, that concrete is a combination of two things. It's a combination of the steel and of the concrete. So how do we explain this? Well, we analyze concrete beam deflections using the method of transform sections. Just as we discussed previously, or in a previous video, in the last lecture, I believe part 1 or 2, we analyze concrete beam deflections using the method of transform sections. So basically, if you have a reinforced concrete beam with steel in it, we're going to transform this into a large block of concrete. Where instead of transferring everything to steel, we're going to transform everything to concrete. So if you have steel here, basically we transform this into a concrete beam that would look something kind of ridiculous like this. Really large like this, with a major jutting out of material where the steel is. Basically, we multiply the area of the steel times the ratio of modulus elasticity of steel to concrete, and we just create a really weird shaped concrete beam that then allows us to calculate the moment of inertia of this thing. Now this gets even more tricky in that there are two potential moments of inertia. See, here's the thing. I have a couple of moments. The thing is, which moment of inertia do we use? Moment of inertia, which to use? Now this may seem strange at first, but let me illustrate this. Moment of inertia, so let's talk about moment of inertia next. Moment of inertia. But which one? And really there are two potential moments of inertia that we might use. The first moment of inertia is the gross moment of inertia. IG, here, well really there's going to be two here. IG would be the gross moment of inertia. So we're never actually going to use this particular one. This is kind of weird. We do something slightly different instead. There are two, we could do that, but that's slightly different and not really exactly apropos. So instead there are two moments of inertia that we need to consider. The gross moment of inertia, and this is the moment of inertia of just the concrete, ignoring the steel entirely. Just the concrete, ignoring steel entirely. So if you have a nice rectangular beam, this is very easy to calculate, BH cubed over 12. If you have a T-section, use the method of the parallel axis theorem, get your gross cross-sectional area that way, of just the concrete, ignore the steel. And so this is basically the moment of inertia, treating the entire concrete section as if it's one uniform, nice, strong element. But we have a problem with this though. As we previously discussed when we look at the strength of concrete, we said that concrete cracks. We said that and really this needs to happen in order for the steel to be fully engaged. And so we usually say, okay, well, concrete needs to crack. And the thing is, if it's going to crack, it's going to crack suddenly if it's cracking down here. For example, if you have a beam in positive bending, so cracked moment of inertia, and this is going to be ICR, the cracked moment of inertia. The cracked moment of inertia. Well, if you have a concrete beam and you put it under positive bending, well, it of course is going to crack. And so there's going to be all these cracks along here, and this is perfectly fine because the steel is holding all the tension, not the concrete. But this portion of the concrete member down here is no longer even in contact with each other. You'll have this plane of concrete will no longer even be physically coupled to this plane of concrete here. This will be being held together. This will be held together with the steel rather than the concrete. Now this part up here, the top of the beam that's not cracked, this is going to be still in physical contact. It's going to be connected in bearing, and so that part will still be contributing to the moment of inertia. But the concrete down here will not. And so here, instead, we're doing something different. We need to have a way of considering this. And so ICR, we are going to use a transform section. Do use transform section, combining two elements. Basically, we're saying with ICR is the cracked moment of inertia. The cracked moment of inertia. And this is where effectively this is where we consider two things. Consider the I. Well, we ignore any I given by the concrete intention. Because it's cracked, it's not even touching each other anymore. Ignore any I, moment of inertia, from the cracked concrete, from the tensile area of the concrete, the tension region of the concrete. And instead, we use two things. We use an I made of two pieces. One, the Whitney stress block of the concrete. So we'll look at just the Whitney stress block. We'll look at the section down to just the depth of the Whitney stress block. Whitney stress block. And two, the transformed area of the steel. So again, you'll end up with something like this, where if you had a steel section, if you had a stress distribution, something like this, if you had let's say you had something kind of like this, you have your Whitney stress block with your 0.85 F prime C down to a certain depth, and then maybe you have a point force of steel here, your T here, which is equal AFY basically. But we're going to then treat this as a section made up of two things. For deflection, to calculate the I, we'll use the concrete down to the depth of the Whitney stress block, this concrete here, the compression region of concrete, and we'll also have a element of steel here, but it's going to be transformed. It's going to be increased far beyond its original area by multiplying by n. So this has an area, the same depth. It'll be the same depth as the tension steel, the center of the tension steel, but the area is going to be equal to n times area of steel, or where n is just ES over EC. So it's basically ES, the modulus of elasticity of the steel, 29,000 KSI, divided by EC, the modulus of elasticity that we calculated previously for the concrete. So you basically combine these two things together. You get two different areas, and you just combine them with the using your parallel axis theorem. And you can just treat this like a point line, a line area. Treat it as a single depth. You could calculate the local moment of inertia of that, but you can just use the AD squared, and that would be close enough for that. Okay? So effectively, when we look at the initial deflections of concrete beams, we have two extreme cases. We have two basically extreme cases. Two extremes. One is the deflection from I gross, one the IG, so that'd be kind of a lower bound on the lower bound. And two would be the I cracked, the cracked moment of inertia, the deflection that you would get from the cracked moment of inertia. And this is the upper bound, so higher. This would be a lower bound for delta, the lowest deflection you would get, and this would be the upper bound for delta, the highest deflection you would get. So this is kind of the lowest moment of inertia you'd have, and this is the highest moment of inertia you have. This is the moment of inertia you have before you apply a single pound of load to your section, and this is the moment of inertia you have after everything is cracked to hell and back. It's already, you've taken that beam up to the maximum loading right up to the point of collapse. That's kind of the other extreme. And in reality, we'll be looking at some sort of interpolation or some case somewhere between these two extremes. So instead, what we use for the code approach, the moment of inertia code approach, sort of combines these two together. Moment of inertia code approach, or the ACI approach. A code approach we use the following formula. And actually I might do this on the next slide so I can write all these things out. I want to put all this in one slide so it's all nice and together. So, but it is going to be a sort of interpolation, or maybe not a direct interpolation, but it is a combination of these two. So moment of inertia code approach code approach. And the formula here, well, first of all, this is formula 24.2.3.5.a. Let me get you a page number for that. Well, it's going to be equation, let me write out the formula first. That would be good. This is going to be, the formula is IE, I effective, is going to be MCR divided by MA, and I know we haven't talked about some of these yet, but I'll define all these and discuss them, times IG, and this to the third power, times IG, plus 1 minus MCR divided by MA to the third power, and all this times ICR. And this here is 24, this is equation 24.2.3.5a, point A. And the page on there, 24.2, let's see, okay, at least in my manual, this is also on page 400. But it may vary slightly for your text, or for your code. Okay, now, let's see here. Let's define all this nonsense. Well, exact opposite of nonsense, actually. IE, this is the effective moment of inertia. And this is what you really want. This is what we've been working up to. This is the effective moment of inertia. Again, it's going to be somewhere between the IG and the ICR. We're kind of interpolating between these. It's not a linear interpolation, but it's more of a cubic interpolation, effectively. So the effective moment of inertia, and this is what you'll feed this into your deflection equations. Like what we saw previously, the deflection, by deflection equation, I mean, the deflection of a distributed load on a simply supported beam, or the deflection of a single point load caused by a single point load on a fixed beam. Any of those deflection equations. So you feed this is the moment of inertia you're actually going to use in your deflection equations. IG is the gross cross-sectional area, as we discussed. Sorry, not cross-sectional area, gross moment of inertia. The moment of inertia of the gross concrete cross-section. If you're fortunate enough to have a rectangular beam, this is just BH cubed over 12. Moment of inertia of gross concrete section. The ICR is the cracked moment of inertia, and we've already discussed that. The cracked moment of inertia. And then MA is fairly straightforward. This is the applied moment. This is the applied moment. And I believe we talked about MCR again, but I believe we've talked about MCR before, but I'll remind us here. This is the applied moment, the actual max moment present in your beam. You know, BH cubed over, not BH cubed over 12, WR squared over 8, PL over 4, whatever you have. This is the actual applied moment, the maximum factored moment of the beam. Well, actually, sorry, not factored moment, unfactored moment. These are service loads. And MCR is the cracking moment. MCR is your cracking moment. Cracking moment, okay. So I do want to describe this a bit. We have our, I can't recall if we've talked about this before, but I'll just go ahead and repeat it here. MCR is the cracking moment. This is the last piece that we need for our initial deflections. MCR is the cracking moment. And MCR, the formula for this, is going to be FR. And this is basically the a moment that must be applied to the beam in order to cause cracking or in order to mobilize the steel. So MCR is going to be equal to FR, the modulus of rupture, times IG divided by YT. And this is equation 24.2.3.5b. And that's also found on page 400, at least of my edition of the manual. And where FR is the modulus of rupture. And this is something you can actually directly measure from a lab test, but like most things in the ACI code, we usually just use a formula where we can calculate this from the F prime C value, because that is the main mechanical property of concrete that we tend to calculate everything else off of. This is a material property, the modulus of rupture. And the formula for this, FR, is equal to 7.5 times lambda F prime C. Times the square root of F prime C, where again F prime C is your concrete strength, your concrete compressive strength, and this is formula 19.2.3.1. And then if I go to that formula, 19.2.3.1, we can find lambda, and lambda is a factor for lightweight concrete. It's a modification factor for lightweight concrete, and lambda, if I haven't explained this previously, is a modification factor for lightweight concrete. Usually we're not going to have to worry about it, but sometimes we do. So you would modify this if you're dealing with lightweight concrete. And so it's a modification factor for lightweight concrete, and this can be found depending on the cases, that sort of thing. It's actually described in a table, and lambda is described in table 19.2. Wow, if I can write the word table properly. Table 19.2.4.2. And there are different cases depending on this, but if you have normal weight concrete, lambda is just 1.0. So in most cases, if we're dealing with normal weight concrete, as we do most of the time, lambda is just 1.0. But if you're dealing with any kind of atypical, unusual concrete, then you'll need to go into a higher level, do a little bit extra work, and make that function there. And the last thing we need to be aware of is YT. YT, now thankfully you don't have to do another equation, it's just a section property effectively. YT is a distance. It is a distance from the centroid. Not really that difficult to calculate. It is the distance from the centroid of the gross cross-section to the tension face. To the tension face, ignoring the steel. So it's not to the so it's not the depth to the steel, but it's the depth to the tension face. And maybe I'll illustrate this with some examples in case you can't grok that. Ignore steel. Grok is a great word. Okay. So YT, let's say you have a nice rectangular beam. Well, maybe your steel is here, maybe your tension reinforcement is here, and your centroid, the centroid of the gross cross-section, again, not the centroid including the steel, but the centroid of the gross cross-section might be there. So assuming this was in positive bending, now if it weren't in positive bending, that would be different. But if it were in positive bending, this would be the tension face. So the YT would be like this here. For positive bending, and if you had negative bending, YT would be this distance here. YT would be negative for negative bending. Now for a rectangular cross section, it's going to be the same for positive or negative, because again, this is based on the gross cross section. But then if you have something like a T-shaped beam, this is where things get interesting. So I haven't talked a lot about T-shaped beams, but they're not too difficult to work with. I would like to put together a video on those if I have time this semester. So again, it's going to be the centroid. It's still going to be the centroid of the gross cross section. So if you have, this is positive bending here, the centroid here is not going to be at the middle. It's going to be more like right here, something like this. So your centroid is going to be something approximately like that. And so here, the YT would actually be different, very different, depending on whether you're dealing with positive or negative bending. It'd be much larger for the positive case than the negative bending case. This is the YT for negative bending. Negative bending, again, where the top is in tension, the bottom is in compression. And positive bending, the opposite, our normal bending. And this would be YT for positive bending. And really, this is it. So, these are the formulas we apply for initial deflection of concrete beams. We get our YT, we get our cracking moment, we get our applied moment, we get our initial, we get our gross and our cracked moment of inertia. Again, cracked moment of inertia using, cracked moment of inertia using a method of transform sections, including the Whitney stress block, etc., including just the Whitney stress block and the steel. And that's it. We run through the equations. It's pretty much just plug and chug, and hopefully this isn't too bad. Long-term deflections is something we'll talk about in a bit, but this is really all you need to know in order to calculate the initial deflection of reinforced concrete beams. All right, that'll do it for this portion of the lecture, and as always, thank you.